Please, Antonio.
Thank you. So, mirroring. Yes. So let me start by thanking Andreas for this very interesting idea of a retrospective meeting. There is a lot to learn about, and we have all been very hectically working on, doing whatever, using whatever tools we had in the lab to address this urgent need. The first studies in Bellinzona go back to early serologic analysis in 2020. And I just want to show to make a couple of points with this slide. So first of all, the antibody response is variable in different individuals, and it's higher in patients which have a more severe course, possibly because there is more antigen. But even in these groups, the response is spread over at least 2 logs. So we all have a very different capacity to make antibodies in response essentially to the same pathogen. The second finding is that the RBD response is really immunodominant and accounts for 90% of serum neutralizing activity. If you absorb RBD antibodies, the neutralizing activity drops by more than 90%. Now, the RBD antibodies decline with a half-life of 50 days. This was a lot of discussion and even panic, but this is pretty normal. We know it's a characteristic of the response. However, during this decay, the avidity of the antibody increases. And then, this work led to mapping of several monoclonal antibodies on the ACE2 binding site that's called RBM. Subsequent studies where we looked at single B cells and serum antibodies really confirmed that while the total antibody response decreases, the frequency and the avidity of single B cell increases with time, while the titer of the antibody decreases, but however, the avidity of the antibody increases. And this was the time when we finally had a vaccine in our hands, and we could show that the vaccines, which use stabilized prefusion proteins, induce primarily antibodies to the prefusion spike, while the infection induces a lot of antibodies against post-fusion, which, as you imagine, do not have any neutralizing activity. The antibody avidity, of course, as I mentioned, rises over time, and this creates a resilience to the escape by SARS variants. Now, we were involved with SARS many years ago in 2004. At the first SARS infection, I had the possibility to study a patient who recovered from SARS infection. And so we had this idea of revisiting serotherapy. We developed an efficient method to make antibodies from memory B cells by combining EBV with the TLR agonist. And so we got the idea of just capitalizing on going to those rare individuals that make a particularly good antibody response, screening the antibody produced, and then making the antibodies in the lab for therapy or prophylaxis. The advantage of this approach is that you can use whatever screen you like, including functional assays for screening. Now, there was no traction at the time to develop SARS antibodies, so I froze down some vials from these individuals for some time. Now, we learned a lot about the selection criteria to identify protective antibodies, and I think I summarize in 3 aspects. The first is the potency, which means an antibody effective at low doses, capable of neutralizing at low concentrations. The second is the breadth. So if you have an antibody that can neutralize different related viruses, it means it recognizes a conserved site, and this creates a resistance to immune escape. And we have examples of this for several viruses. And finally, we realize that it is important also the effector function that can play a protective role in vivo. So these are infections that we have studied, and some of these antibodies, including this sotrovimab, have been in humans, and I will elaborate a little bit more about that. Now, I want to use the influenza just to make the point that there are different classes of antibodies. We have to balance potency, breadth, and effector function. For instance, antibodies to the so-called globular head of the influenza hemagglutinin are immunodominant. They block binding to salic acid, so they're potent neutralizer, but they select escape mutants very easily, even in vitro, and do not trigger effector function. In contrast, antibodies to this conserved site in the stem are less potent, but neutralize, in fact, most, if not all, viral subtypes, and most importantly, do not select escape mutants and do trigger effector function. So again, mechanism of protection, shall we go for neutralization or effector function? And I just want to, again, remind you that it's always worth to go back in the literature. There are early studies by the group of Walter Guerin showing that pulmonary influenza infection in mice can be treated using antibodies that have very little in vitro neutralizing activity, suggesting that effector function would be important. And this more recent study from the Vir group indicating that neutralizing activity of antibodies is, of course, a proxy of in vitro protection and viral neutralization, but varies widely depending on the target cells that you use for neutralization. For instance, whether they overexpress TMPRSS2 or ACE2, TMPRSS4 or ACE2. Now, with regard to effector function, I think this is a textbook picture. Could be clearance or opsonized virions. Most probably, the most important function has to do with elimination of virus-infected cells by so-called ADCC or ADCP, and potentially even increased antigen presentation to T cells. But one of the interesting aspects is that now these function can be engineered in or out of recombinant antibodies. For instance, you can make antibodies that don't bind to the Fc receptor, neither to complement, by engineering the LALA or GRLR mutation. You can increase binding to Fc gamma receptor 3 to NK cells by glycoengineering, for instance, afucosylation. You can modulate binding to 2A and 2B by inserting selective mutation in the Fc, and you can increase the half-life by increasing binding to FcRn. Now, we know, of course, that the effector function is for IgG is particularly high for IgG1 and IgG3, but beyond the isotype of the antibody, what is important is where the antibody binds on the antigen. And of course, this can be measured only by measuring binding to virus-infected cells. So what we find in 3 different systems, influenza, RSV, and SARS, is that antibodies that bind on the top, on the globular head, on the top of the RSVF, or on the so-called RBM, the receptor binding motif, are very potent neutralizers but do not have effector function, while effector function is limited to antibodies that bind on the side to the HS stem, to the stem of the RSVF, or to this site, the so-called site 4, which is recognized by S309 or sotrovimab. Another antibody that induces effector function is this anti-stem helix. So you see antibodies that bind on the side are characterized by effector function. So The S309, the sotrovimab, was isolated from that vial that I put away in 2004 from that individual. So that individual was infected by SARS-1 and developed very good antibodies that cross-react with broadly with sarbecoviruses. The site 4 is more conserved compared to the RBM. It was a surprise that the RBM would be so plastic. And as I already mentioned, this antibody elicits potent effector function. So this is the first list of antibodies that were used for prophylaxis of therapy of SARS in humans. And most of them were chosen for high neutralizing activity and for their capacity to interfere with ACE2 binding, so for capacity to bind to RBM, while sotrovimab does not interfere with ACE2 binding, but still has moderate neutralizing activity, but effector function. Now, when there was this dramatic shift of the virus with the emergence of Omicron variants, the antibodies most antibodies, in fact, all of the antibodies that recognize the RBM lost neutralizing activity, but sotrovimab, or S309, as you want to call it, showed a reduction of neutralizing activity, but was still capable of neutralizing the mutant viruses. Now, if you look more in practice, there is about 100-fold decrease in the worst case of neutralizing activity. And this decrease in neutralizing activity is reflected by decreased affinity as measured by Fab binding. However, the IgG antibody still binds very well to Omicron-infected B cells, cells, because of the avidity. It can bind, it's a bivalent and can have avidity. And in fact, if you measure ADCC, there is virtually no difference between ADCC elicited on sotrovimab infected cells and that elicited on XBB1 infected cells. So, in other words, ADCC is less dependent on affinity as compared to neutralization. You see there is a relatively good correlation between binding affinity and neutralizing activity, but binding affinity doesn't matter as far as ADCC is concerned. Now, in a mouse challenge model, you can see that in spite of a 90 or almost 100-fold decrease in vitro neutralization, the antibodies can still perfectly protect mice, and this antiviral effect is reduced by mutation that abolish Fc binding. Now, the efficacy, these experiments were confirmed by other laboratories showing that sotrovimab is effective against in hamsters and macaques against BQ11, and in humans there were observational cohort studies that confirmed that sotrovimab was as effective as the drug in early therapy of patients. So if you are interested, you can look at this opinion article written by a British scientist, which suggests that WHO should also consider or reassess the guideline to evaluate monoclonal antibodies for therapy. At the same time, it's true that FDA has recently approved an anti-SARS antibody just based on the capacity to mediate in vivo neutralizing titers. So I don't know whether effector function at some point will be considered, but certainly the data so far confirm that there is a potential effect. Now, coming back to the same study that I just mentioned, we looked into the plasma antibodies elicited either by vaccine or disease. And in spite of a much reduced activity, neutralizing activity of the plasma, we find that the binding of the IgG to infected cells, and more importantly, the IgCC, is perfectly conserved. So this suggests that the antibodies induced by infection or vaccination could still be effective on these new Omicron viruses and can confirm some level of protection that I think we can witness in the population. Now, before finishing, I just want to touch on two other aspects. This is a study that was published in 2019 where it was a collaboration with David Wiesler, showing that surprisingly, antibodies to the RBM can trigger fusogenic rearrangement because they mimic the viral receptor. So if the virus is already ready to fuse, so has already been activated, the antibody binds and triggers the fusogenic activity, and this way inactivates the virus. It mimics the receptor. This is a function of most, although not all, RBM binding antibodies. And to finish off, I wanted to come back to the study by from Federica's laboratory, where they were looking at antibodies that would be broader and broader and broader, and then eventually identified antibodies that neutralize both all coronaviruses. And as you see here, the antibodies recognize the fusion peptide. And the fusion peptide is hidden inside the molecule. So there is a complete clash in binding. So it cannot bind to an intact molecule. But what you see here is that if you look at infected cells on the y-axis, the binding of the antibodies can be promoted by the by the adding ACE2 or adding other activating antibodies. So the model is that this epitope is cryptic and is available only when the RBD binds to ACE2. It opens up this region, probably for proteases as well as for binding of this very broadly neutralizing antibody. The other aspect that was came up in this study is that if you look at the UCA, the unmutated common ancestor of these broadly reactive antibodies, you see that some of these UCA react with a single common cold coronavirus, and through somatic mutations, they acquire breadth and as well as higher affinity. So this again shows that this broadly reactive antibody built on the continuous selection upon exposure of new viruses and somatic mutations. And so I'd like to close here just summarizing. We have different classes of SARS-CoV-2 antibodies. The anti-RBM are potent neutralizer. They can trigger fusogenic rearrangement, lack effector function, and they are very susceptible to viral escape. There are just a couple of antibodies that have been described more recently that appear to be more resistant because they essentially mimic ACE2. The site 4 on the RBD and the stem helix are relatively conserved, and the antibodies to these sites have potent effector function. And finally, fusion peptide antibodies are highly conserved but poorly accessible. The other thing we learned is that effector function, of course, can play a protective role, but more importantly, there is no evidence for disease enhancement. This was a topic that was highly raised a lot of concern at the beginning, and in fact, there is no evidence. That I should say that probably the only solid evidence of enhancement relates to dengue antibodies. The other thing is that monoclonal antibodies have really demonstrated that they can have both prophylactic and early therapeutic activity, not late therapeutic activity, unfortunately, in SARS. We have gained insights into biology of primary, secondary, and memory responses. I mean, we just heard fantastic talks this morning. And in general, they paved the way to what we call now the pandemic preparedness that I hope will not be forgotten as we tend to forget things that we don't like. And so with this, I just want to tell you that the work comes both from the Sallusto and Lanzavecchia laboratory, which is now spread a little bit everywhere, and from the team of Davide Corti at UMABS and Vir Biotechnology in Bellinzona. So thank you for your attention.
Thank you so much, Antonio, for the beautiful talk. Is there any questions? Any comments? Andreas, there is one over there.
Great, as usual. So would you now argue that, okay, we can forget all these in vitro neutralization assays? Because anyway, yeah, sometimes you're lucky and then...
No, not at all. I think it's still the best proxy of protection, viral neutralization. But when you set up a neutralization assay, you tend to optimize because you want to see a good signal. So you use target cells that overexpress, for instance, ACE2. And this will tend to favor some antibodies and disfavor others. I think we should look at neutralization not like the gold standard, but still like something that, you know, can deliver different data depending on the assay.
On that actually, yeah. So do you think it's the same for systemic and for mucosal immunity?
Sorry?
Do you think it's the same for systemic and mucosal immunity? I mean, in the mucosa, you just have the antibodies versus...
No, we had
a body you have in blood, you have the cells and so on.
Absolutely. So there are, you know, as we have heard previously, and probably even broader, depending on the site, you have different proteases around and different accessory receptors, and so yeah. Once again, we have to go back to the viral biology, which is unfortunately not very simple, as we have heard.
So the conclusion would be that neutralization in vivo assays are informative as long as these antibodies are really on the mucosa.
Well, of course, you would like to have the neutralization, the mucosal antibodies, but that's I hope somebody will address this issue. You want to probably at the end of the day, you want to decrease by 1 log viral infection, and you are fine. You are not going. This will be the difference between dying and surviving. So the hope is that, you know, even low level of neutralization may be sufficient. Maybe effector function will do the job, and so on. Your point about mucosal versus systemic spread is very, very important, and I don't think we know much about the distribution. For instance, of ACE2 in upper versus respiratory tract. There is a lot known about that, and this will influence the level of infection.
Antibodies need to be binding to the FC receptor N, because that's the only one that can transport
FcRn. Yeah. You can measure IgG antibodies given IV or in the secretions. There are ways to do it in the lungs, for instance. There are ways to do it, and yes, they are present, but the concentration is much lower than in the plasma. So again, it's a matter of delivering the antibody to the right place, and then it takes more time to have them secreted in the lungs. Okay, so in a early therapy setting, time is essential. So probably in early therapy they will act primarily at the systemic level and not at the at the secretary level.
Oh, we have one more question, Winfred.
So wonderful, as usual. Thank you very much. I have a question. You mentioned the importance of antibody-dependent cytotoxicity for virus clearance. And then when we look and when we perform these assays, the assays themselves, they perform very poorly, actually. So we just get a few % of specific lysis. So can you comment on that? Is that on the part of the antibodies? Is that the problem of the NK cells we are using?
That's a very good point. You have noticed that, it was not 90%, it was much less. That's why everybody plots the area under the curve. Looks much better. The results were controlled, of course, by the GRLR antibody. Well, this may be that possibly, again, these are in vitro assays. These are correlates of protection, and maybe the action in vivo is much more efficient. There is also ADCP, which should be considered in the context, for instance, of a lower respiratory tract infection, where alveolar macrophages are very, very important as effector cells rather than, of course, NK cells. So that's a very good point. I think we have to be, I didn't want to be critical on too critical on neutralization. I wanted just to say that, every in vitro assay is subject to in vitro artifacts.
I have another one. You mentioned this these antibodies that recognize the fusion peptide, and that they neutralize. They didn't make it to the clinic. And is there a reason?
For a good reason, yes. They are very poor neutralizers, and there is a very good drug now. I took it 3 times. I got five COVIDs, and 3 times I took the drug. And so the use of antibodies at the moment is limited to those individuals that cannot take the drug.
Only one more question. Here, Antonio. Oops. Here.
Okay.
So you said that the antibodies against the stem part of the influenza, those do not select escape mutants. Why is that?
Yeah, it's very good. The reviewer asked us to take it off from the paper, and when you have a paper almost accepted in Nature, you would agree on everything. But we published that for the RSV. That was also true for the RSV. And was certainly true as far as we tried. This site is very, very conserved. Now, why is it conserved? Because these sites on the side are helices that have to be in one conformation in the pre-fusion and in another conformation in the post-fusion. So they are doubly constrained. And then it's very difficult to make a spontaneous mutation in these helices, because if they fit the pre, they will not fit the post-fusion. So will make the virus unfit. Yeah.
Okay, there is one more last question. Please, Christine.
Antonio,
there is one more question.
one
Sorry.
last question. Taking all the questions and comments together, for the next question, which are the best antibodies to develop clinically, would you argue that at least there should be one against a conserved region to be more resistant to mutations? Because you showed the effect on protection, but these are normally would not be considered at all, because people think when they are not binding anymore and there's no neutralization effect, then they are useless. But you showed it's not the case. Should we make that point more stronger?
So the point is that certainly the most potent antibodies that still people want to develop, I think there is not much space currently for development of neutralizing antibodies, are the ones against RBM. The problem is the plasticity of the RBM and the escape. However, there are a couple of antibodies reported in the literature that appear to be quite resistant to escape, but not yet completely resistant. So it's a lottery. You may, for sure, these antibodies are excellent, but they are always open to an escape. Going for more conserved sites like this helices or the site 4 of RBM is another option, and I don't know really which one to take, and yeah, but that's exactly the conundrum. You know, you go for something very strong with a risk of losing it, or to something a little bit less potent but more conservative. Still, there is no guarantee that it will always work. Huh?
Okay, thank you so much. Thank